this tutorial, we'll be solving a past paper question on the topic of electromagnetic induction. Okay, so this is question 2, and it says a student uses this apparatus to investigate electromagnetic induction. Okay, so the label says the coil of wire. Okay, the poles of the magnet, they are labeled, and there's the terminals of the coil, they're connected to this sensitive ammeter. Okay, you can see that it goes both ways. Okay, the right side and the left side. It further describes when the south pole of the magnet is moved into the coil, the pointer on the sensitive ammeter moves to the left. Okay, so it's moving onto the left side. That means on this side. Okay. Describe 2 ways the student can make the pointer move to the right. Okay, it means that you have to change the direction of the current. Okay, and if you can recall, how can you change the direction of induced current? There are different ways. One of the way is to change the direction of the movement of this magnet. Okay, because if this induced current is produced with the movement of this magnet, so if we change the direction of movement, we'll be able to change the direction of the induced current. Okay, to change the direction of movement of the magnet. Okay, so this is one way. The other way is we can reverse the pole. Okay, so in the photo it shows that south pole is going inward into the coil. What we can do, we can reverse it. To reverse the pole. To reverse the pole. Okay, so instead of south pole going into the coil, now the north pole would go into the coil and it would change the direction of the current. Because the direction of induced current, it depends on the movement of the magnet, or the relative movement of the magnet in the coil, and it also depends on which pole is going into the coil or which pole is coming out of the coil. Okay, so it was a 2-mark question. And then part B. Okay, so in part B it says that the student has a bicycle with a dynamo generator that supplies electricity for its slide. The diagram shows the dynamo, the friction wheel. Okay, this is the friction wheel which presses against the bicycle tire, and when the student pedals, the friction wheel turns and causes part Y to rotate. Okay, so this is part Y, and you can see this part Y is closer to this coil. Okay, so we have a hint now. It's asking in B part I, complete the key of the diagram. Key for the diagram by giving the names of part Y and part Z. So part Y is the magnet. Okay, because in the process of generating electromagnetic induction, there will be a magnet and there will be a coil. So you can see coil, and closer to it, that's a magnet. So this is a magnet and Z is the coil. All right. So this is done. Then B part II. So in this question, this part, it shows the graph of voltage and the time. Okay, so the graph shows the output voltage of the dynamo varies with time as the student pedals steadily. Okay, so you're given on the vertical axis, okay, you have the voltage output, and on the horizontal axis you have the time. So it's asking you state the maximum voltage voltage of the dynamo. Okay, so for this you simply have to read the graph. Okay, so this is 1 volts. Okay, and between 1 and 2 there are 5 boxes, so each box is 0.2 units. So this is 1.2, 1.4, 1.6. Okay, so the maximum output voltage is 1.6 volts. Okay, 1.6 volts, and it could be positive or negative. Okay, because we have 2 peaks. For part 3, it's asking you to calculate the frequency of the output voltage. Okay, so to determine the frequency, what we can do, we can figure out the time for 1 complete rotation. Okay, that will be the time period. So for 1 complete rotation, okay, if we go along the waveform, okay, so it goes all the way up. So this is 1 half cycle. Okay, and then it goes all the way down, and then it ends here. So 1 complete cycle, it takes 0.04 second. Okay, so you know the relation of frequency and time period. Okay, so if you have the time period, you can find out the frequency. So 0.04, so 1 divided by 0.04, this is 1 divided by 0.04. Okay, so this is 25 hertz. So frequency of this dynamo is 25 hertz. Now, which row of the table is correct? Part 4 is asking when friction wheel turns faster. That means the magnet is moving faster. So what do you expect? Okay, you know that the electromagnetic induction, it depends on the relative movement. Okay, so more relative movement means higher voltage. And since it's rotating faster, the frequency of the output voltage would also be higher. Okay, so this is the best choice is C. All right, and next part it's asking, apart from changing the speed of the friction wheel, suggest how the output voltage of the dynamo can be increased. Okay, that means you have to increase the magnitude of induced EMF. Okay, so if you can recall the factor, what you can do to increase the magnitude of induced EMF, you can use a stronger magnet. Okay, so using a stronger magnet, that's one way. Using a stronger magnet, all right, or increasing the number of turns of the coil. Increasing the number of turns in the coil. Okay, so these are the two ways by which you can increase the magnitude of induced EMF or output voltage apart from the speed. Okay, all right. In part C, it's given some more information. The student cycles for 290 seconds. A dynamo produces a constant useful power output of 3.1 watts and is 72% efficient. Calculate the total useful energy output. Okay, so now you have to relate the power output, okay, and the time, and you have to find out the total useful energy output. So if you can recall that power, okay, and energy transferred, they are connected by this equation. Power equals energy transferred, okay, in unit time. So since you have the power and you have the time, you can cross multiply the values of power and time. Power is 3.1 watts, okay, and you have 290 seconds as the value of time. Okay, so energy would be 3.1 multiplied by 290. Okay, so this is 899. Whatever you are getting as your answer, okay, you can write it. So it's 899 joules. Okay, so this is the useful energy output. Now, in next part, it's asking you state the relationship between efficiency, useful energy output, and total energy input. So you know that efficiency is linked with these two in this way. Okay, so total energy input is in the numerator. Total energy input, and the useful output is in the the total energy input is in the denominator, and useful energy output that's in the numerator. Okay, so this is how you would be relating efficiency, useful energy output, and total energy input. All right. In part 3, it's asking you calculate the total energy input. Okay, so you have efficiency, which is 72%. So in place of 72%, I can write 0.72. Total energy input, okay, you have to find this out. Okay, so I can write an X in place of this. And useful energy output, okay, which you have already calculated in the previous part, okay, and it's 899. So 899. All right, so X equals 899 divided by 0.72, which is equals to 899 divided by 0.72. Okay, so this is 1248.61. Okay, so I can write 1250 joules. Okay, so this is it. And in the next tutorial, we'll be solving more questions on electromagnetic induction. Thank you for watching.